Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to go ahead and start by building up the formation of full molecular species. And in order to do this, we're going to go ahead and start by looking at the very nature of the bonds that hold atoms together. So we're going to go ahead and try and develop how this can go ahead and turn into the general structure of molecules. So first, we have to look at how these bonds hold atoms together to form full molecular species. What are the different, essentially, building blocks of how bonds are made? Then from this, we can go ahead and build up a full nomenclature of how do I refer to certain types of molecules. And this will also help let me build into the types of molecular formula used for both ionic species and covalent species. Then, once we have our nomenclature, we can go ahead and use the Lewis structure shorthand to depict our molecular structures. And one of the best ways to try and figure out whether you've made the right Lewis structure is to help use formal charges to determine which of the structures you made is essentially the most stable. However, Lewis structure formalism is a two-dimensional form, and molecules are three-dimensional. So we're going to have to go ahead and take our two-dimensional shapes and help use this to inform three-dimensional systems. Then we're going to go ahead and finish by using our electronegativities and our three-dimensional structures to tie them together to develop the property called polarity. And this will help inform a lot of what behavior molecules have on a macroscopic scale. So let's go ahead and start by looking at those molecular bonds. So when we're looking at molecules, one of the big things to remember here is that we need to find a way to tie together individual atoms. So how do we do that? And that's really where it comes down to electrons, because we can think of our atoms really as big old nuclei, so positive charges, and they're going to be tied together by electrons. So if I've got two nuclei, they have positive charges, and I've got electrons in the middle, this means that this positive charge, while it hates this positive charge, really is staying in it for the kids. So it wants to hang out near the electrons. And so what we find is that these negatively charged electrons help pull together our positively charged nuclei. And this is what's called a Coulombic interaction. So Coulombic interaction is the general term to say positives attract negatives, negatives attract positives, but positives hate positives. So what we're really relying on here is the Coulombic attractions to pull together these two atoms. However, the real nature of how these two atoms are tied together are going to depend upon where these electrons are. Are they strictly in the middle of the two nuclei? Are they closer to one nuclei? Or are they really just on one nuclei and this guy just follows along? So if all of the electrons are on one nuclei, this generates what's called an ionic bond, because this whole complex has a net -1 charge. This guy has a positive charge. So that positive charge is going to follow the negative charge. And in terms of a molecular species, what we can do is essentially treat these as paired cations and anions. This nuclei has lost its electron, so it has a positive charge. This nuclei has gained an extra electron. So I've got a free cation and a free anion. And these are going to pull each other together and going to stay as close together as possible. And one of the big things here is that, again, these charges are going to help keep these two ions staying in close contact. However, it's worth noting that this positively charged cation might not necessarily follow its electron to merge with an anion, but will follow simply any anion is as good as any other. And one of the big things about this general structure is now this sodium is fairly happy because it's got a noble gas configuration. This chlorine is happy because it's got a noble class configuration. But the biggest thing is they have to stay together. Otherwise, we have unbalanced charges. And a big feature of these Coulombic interactions is you want the overall system to be charge neutral. However, it's worth noting that you can expand this process not to just describe one or two atoms, but 3 or 4 more atoms. So for example, we can go ahead and imagine something like calcium. It wants to lose 2 electrons, but there might not be any atoms out there that wants to accept 2 electrons. So it's going to go ahead and give 1 electron to one chlorine and another electron to a different chlorine. And this will end up generating a calcium ion with its positive 2 charges, and now 2 chlorides with their own negative charges. Now this calcium should be bound to each of these chlorides. And one of the big things is that now I've got a bond of differential charges in between the calcium and both of these chlorines. And it is worth noting that, again, one of the big differences in between something like sodium chloride and calcium chloride is calcium chloride has a positive 2 charge, which means it has a larger charge, so it's going to attract the negatively charged anions more. And in general, we're going to see that the larger the charge, the stronger the attraction. However, it turns out ionic bonds aren't the only way to coordinate 2 atoms. You can also imagine a system where you've got 2 nuclei, but they're the same nuclei. So the electrons aren't more attracted to one species versus another. A great example of this is hydrogen gas. So in this case, I've got one positively charged hydrogen atom, one positively charged hydrogen atom, and those 2 electrons staying smack dab in the middle, bouncing back and forth in between these 2 H atoms. In this case, what we find is that the electrons are going to be fairly evenly shared. They'll equally be on this hydrogen atom as this hydrogen atom. They're going to move back and forth very evenly. Now, since these 2 electrons are perfectly shared, what we end up having is what's called, since the electrons are shared and not just on one atom or another, this is what we call a covalent bond. So a covalent bond means electrons are shared. However, because they're shared evenly, this is called a nonpolar species, as the electrons don't build up on one pole or the other. They're evenly split. So again, covalent means they're shared. Nonpolar means they're shared evenly. However, you can imagine a system where the 2 atoms are not identical. So what would happen if I've got, say, not just 2 hydrogen atoms, but a hydrogen and a chlorine atom? Well, it turns out that chlorine wants those electrons way more than hydrogen has. So they're going to go ahead and pull the electrons to spend more time on chlorine, which means as a whole, since the electrons are spending less time near the hydrogen atom, it's going to have a slightly positive charge because it looks more like a proton than an actual hydrogen atom. Meanwhile, the chlorine atom looks more like chloride than it does a strict chlorine atom. So it has a slight negative charge. And it's going to be worth noting the electrons are always going to be pulled towards the more electronegative atom, because the more electronegative an atom is, the more it wants electrons. So this should follow fairly evenly. And so because the electronegative atom builds up this slight negative charge, often represented by this lowercase delta sign, this ends up generating what we call a polar bond, because all of the electrons are pulled to a single pole. And what we tend to find is the greater the difference in electronegativity, the more the electrons are pulled to one atom versus another. And this generates a greater charge difference. And one of the big features here is that when we're looking at this idea of ionic versus covalent, realizing that it isn't exactly like atoms end up in bonds end up in one category or another. It's really a continuum. On one end, we have nonpolar bonds where the electrons are shared evenly, and on the other, where one atom has all the electrons. However, polar covalent really essentially encompasses the gambit. However, because as humans, we like to put things into nice even boxes, we tend to, again, split up the bonding type based on the difference in electronegativity. If 2 atoms have very similar electronegativities, we call them nonpolar. And the difference we often settle on is about 0.5. So for example, carbon at 2.5 and hydrogen at 2.1 tend to form what we call a nonpolar bond. However, when we go to hydrogen and nitrogen, this has a difference of 0.9, so we call it a polar bond. And by the time we get to, say, fluorine and sodium, or chlorine and sodium, now we have differences greater than 2, and so we call it an ionic bond. However, it is worth noting that we tend to oversimplify the system. So generally what we tend to think is that if I've got any metal mixed with anybody essentially on this non-metal portion of the periodic table, so think essentially carbon through iodine, we tend to call these ionic bonds, even if that's a little bit of an oversimplification. If we have neighboring atoms, these, as a general rule, tend up to be nonpolar, but there are plenty of exceptions. And if we have atoms that are essentially 2 spots away or more on a periodic table, again, with a special caveat, if you follow diagonal, these tend to be fairly similar. But if you say go from carbon to germanium, or nitrogen to arsenic, or carbon to oxygen, we tend to call these polar. So these are some oversimplifications, but they tend to be a pretty good description of when somebody tends to be ionic, opposite sides of the periodic table, polar, slightly separated, or nonpolar, essentially close neighbors. But this is all dictated based on electronegativity. The more electrons are attracted to one species versus the other, the more likely we're going to reflect this in the very nature of the bond and thus the molecule. So this gives us an idea of the base components of bonds. Next time, we're going to go ahead and dive in a little bit more into the character of ionic species. Until then, take care.